Good morning. For those of you who do not know me, my name is Alain Durand. I'm going to give a talk on what's going to happen after IPv4 address completion in a broadband type environment. And this is all about sharing IPv4 addresses. The point is, we have to make sure that's our responsibility, that the internet will keep growing, and that this growth will be disconnected to the upcoming event, which is the IPv4 address exhaustion. Disclaimer about my company, I've made no decision whatsoever to deploy any of the following technology. I think until the day this is in the network and we have customers running on this, we will still keep this disclaimer on any slides we will present. There's a technology known as dual stack light. This is essentially combining two existing technology, which is NAT and tunneling. It's not that we love NAT or we love tunneling, but those are technologies that have been around for quite a while, and somehow we understand how to operate them, and we have some interesting results by combining the two. So there's a bunch of other slides on this technology that I've presented in this forum, in a previous landing talk, or at IETF, and for the sake of time, I'm not going to go in every single detail, but just two diagrams to illustrate what this is about. So there are two scenarios where you can use this kind of technology. You can use it in a home environment, for example, when you have a bunch of legacy devices like legacy PCs or legacy webcam or legacy consumer electronic device who want to access the internet. And you cannot change everything to IPv6. And the content on the other side of the internet is not going to migrate to IPv6 until quite some time. Maybe the most important site, like Google, may migrate sooner than the others, but it's going to be a very long tail of sites that are going to stay on IPv4 for quite some time. So the idea is to focus on the home gateway in that case and try to do things there. So the way it works is very simple. Is that this new home gateway, instead of doing translation from a private IPv4 address space to a global IPv4 address, is going to take the packet from the inside of the network and tunnel it, no translation whatsoever, tunnel it to some place that can essentially aggregate more customers on the same IP address. So if you look at the life of a packet, it's pretty straightforward. Let's say a PC wants to go to the NANOG website. It has a local address, 192.168.1.3, and try to go to 198.108.95.21 on port number 80, source port number 1001. So this packet goes from the PC to the home gateway, and home gateway is going to encapsulate it into a v6 packet. So this v6 packet has the v6 source of the home gateway, and it has the v6 destination address is the IPv6 address of a tunnel concentrator. So in this model, the home gateway has no global IPv4 address whatsoever. The only thing it has is a v6 address. So at the point where you have very little or no more v4 address to give to a customer, you can simply give them this home gateway. Home gateway sends a packet. Packets arrive in v6 to the tunnel concentrator. So it's the same box that does two things, tunnel concentrator and NAT. So the tunnel concentrator removes the IPv6 header, remember the v6 source address of the tunnel. Now it has a v4 packet and simply does a NAT v4 to the outside. So what's important is the binding table. Well, it's normal NAT binding table that has been extended to also remember that was the v6 source address the packet was coming from. So when the packet gets back, you can recreate the tunnel. So there's no state whatsoever associated with the tunnel, if only what is in the NAT binding. You can also deploy this technology, this tunneling technology, straight from the end host. And this is something that is really interesting in environments, for example, like wireless, 4G, 3G, always-on environment, where you have a lot of devices. There's no home gateway whatsoever. They're all directly connected to your network. And you only have IPv6 addresses to handle to those devices. Well, we do exactly the same thing. When this node wants to send a v4 packet, it creates a v4 packet, and it encapsulates it into a v6 packet. Ship the packet to the tunnel concentrator. Same thing, tunnel concentrator decapsulate. There's a v4 NAT behind, sent to the other side. The trick here is that the IPv4 address that is embedded in this packet is meaningless to the NAT, because what really matters in the NAT is the v6 address of a tunnel endpoint. So we can essentially give the same v4 address to every single of those wireless devices. So we have asked IANA to reserve an IPv4 address for that, something like 192.0.0.1 or something similar. So what's the status of this technology? Well, there's a draft that has been combined from different proposals that came earlier in IETF. This is now in the software working group that has been officially rechartered to do that, to standardize this technology. So this is not a technology for my employer. It's not a Comcast technology. We really want to push this as an industry-wide technology. And the target to get this, at least the basic spec of this, standardized, is very aggressive. It's first quarter 2009. And the reason it's very aggressive is that the IPv4 address exhaustion is not going to wait for the IETF to do its job. So we really want to get this off the ground as quickly as possible. We already have implementation of this. We took a Linksys router and we took OpenWRT and have some folks creating a module for OpenWRT, and it works. We also have carrier-grade NAT code to do the tunnel encapsulator and NAT. We use some vendor code, and we already have started some open source projects. So if you are interested by any of that, please contact me offline. I have this in my office, and except from the UPnP stuff, most of it just works. It's not perfect, it's like NAT is not perfect, but if you want to do mail, web browsing, and streaming video, it's no worse than current situation. So it's a tunnel-based situation, and tunnel-based solution. So there are a number of things we can do with a tunnel. The first thing is we can point the tunnel wherever we want. So this carrier-grade NAT, we can put it in our network wherever it makes sense. In some cases, it makes sense to have it very close to the edges, to the first hop router. In some places, it may make sense to pull this traffic further into the network. And we can also slice and dice this whichever way we want. We can say, oh, the tunnel endpoint is discovered through a DHCP option. So we can say those 1,000 users go to this tunnel endpoint, to this carrier-grade NAT, this 10,000 users over there go to another tunnel endpoint first another NAT. So you can scale horizontally this as much as you want. You don't need to have a big router that is going to do this for you. You can have much, much smaller machines and size them whichever way makes sense. The third thing that can happen is that the tunnel does not need to end into the service provider network. It can end anywhere. So there are two cases where it's interesting. The first case is you are a new service provider. You have absolutely no v4 addresses left. Well, you can subscribe to a third-party service that's going to run this stuff for you. Somebody who has v4 addresses and can run this translation for you. Or if your customer don't like your carrier-grade NAT, well, they can point to somebody else. It's kind of creating an open market for us. So users are not going to be locked in a walled garden by this stuff. One of the things that Randy brought as a very, very important point is about what is happening with application-level gateways. And it's true that some applications require application-level gateways to work through a NAT. And the question, and I'm quoting Randy again, is not so much where the NAT is. It's who has some control on it. Who can know what are the port bindings that are in use. Because the packet being modified somewhere or modified somewhere else doesn't really matter as long as the customer is able to insert his logic. And so that two customers who wants to deploy a new application can get together and agree that they need to do this in their part of the network without having to touch the core. We can do that by enabling the end node of the home gateway to perform this ALG function, not put it in the core. Doing ALG is really hard. Doing them in the core is going to be a big mistake. It's much better to offload this to the edges. But to do that, we can do it and keep the NAT function in the core. There are two ways we can do that. We can have dynamic reservation of port, or we can have static reservation of port. Static is the simplest thing. We could have, for example, a web page where users goes and says, I would like to reserve 5 mappings, and there come some IP addresses and some ports associated to them. And you can just copy those and use them. It's no different from today you go to a web page on your home gateway and says, oh, I want to forward port number 80 to my machine. The only difference is that you may not get port 80 because a lot of users are going to share the same address, so port 80 is going to be very popular. The other thing we can do is there are things like UPnP or NAT-PNP that automatically create bindings, where we can have a relay of those and create the binding dynamically into the carrier-grade NAT from the home gateway. And we are looking at protocol like NAT-PNP to do that. Some of the things we'd like to avoid is Having something that's very complex is going to take 5 years at IETF to standardize. Because if that happens, we can just all go home and this is not going to solve anything. Redefining DHCP-v4 is clearly in my things of list to avoid. Anytime we touch DHCP, it takes 3 years. It took us 3 years to really develop DHCP-v6 through bake-off, through financing code, through having people on open source and product to come up and iron out all the bugs. So this is going to be way too long. Another thing we really, really don't want is to take the IPv4 default free zone routing table that has 260-something thousand entries, as we learned yesterday, and import this to IPv6. Because the v6 route is 5 times longer than the v4 route. So if you do that, you will have an interesting problem on your routers that do not have enough memories on the TCAM. So that's really something we like to avoid. And we also like to avoid inefficient port allocation schemes. It's something to say, in average, users consume, let's say, 1,000 port number. It's very different from saying, I'm going to give 1,000 port number to each user. UPnP is going to be a serious issue. The semantic of many applications using UPnP is, I want port number 6,000, and whoever has port number 6,000 in my house is going to go away, and I'm going to take its place. And please, from router, forward port number 6,000 to me. Well, this doesn't work when you are sharing port numbers with somebody else outside of your household. The NAT PnP semantic is somewhat better. It says, I would like port number 6,000, but if it's not available, I can work with anything else. So please give me any binding external IP address, external port number that I can use, and I can tell my peers that this is what I am using. As long as this binding is guaranteed to stay long enough, then I'm fine. So this seems to be a much better semantic to drive application to. And this problem of port binding, dynamic port binding, is the same for any mechanism that share IPv4 addresses. So you take a double NAT, you take the A+P approach that was described yesterday, you take a NAT64 or NAT-PT applied to a very large environment, you will have exactly the same problem because you are sharing IPv4 addresses, so anything that insists on running on a specific port number is not going to work. And my last issue is about something that really concerns all of us, regardless of if you want to deploy this technology or not. When you are logging things to deal with abuse or lawful intercept or anything like that, today you have a knowledge of the IP address and a timestamp. Somebody from IP address foo has done something bad at T0. Well, if you have hundreds of users that are sharing the same IPv4 address, this information is not good enough. What you need is the information about what port number was used. So there's going to be a need for all of us in the industry to adapt all the tools that we have. When we are logging IP information, we also need to log not only the source port number, not only the source IP address, but also the source port number. And this is true regardless of which mechanism is used to share IPv4 addresses, double NAT, A+P, NAT64, or any other. So that was my last slide. If you had any questions or if you'd like to see some code running, please go talk to me after. I'm here all week. Thank you.
Thank you.